Yeah, my name's Kevin Jernigan. I'm a principal database solutions architect on the Aurora Postgres team at AWS, and I've been with AWS for about 5 years, working on Aurora Postgres. And just want to thank everybody for taking your time, the time today for this session. I know you have a lot of things competing for your attention. Hope you found it worthwhile. There is, of course, a live Q&A or live chat and Q&A going on both in the YouTube and in the Slack channel for this session. So please contribute. Love to have some questions to answer at the end if we have time. So I'm going to talk about global databases and really specifically about global relational databases. And at Amazon, we always start with a customer, and that's where I'll start. Why do customers want their databases to be global? What problems are they telling us they're trying to solve? And along with customer requirements, of course, I'll dive into several ways to make a database global and review the trade-offs for each approach. And then I'll talk a little bit about how we solve these problems with Amazon Aurora. So as I mentioned, I've been with AWS for almost 5 years, and I've been working with relational databases for more than 30 years. I started my career way back in the late 1980s with Oracle, but then I was an independent consultant through the 90s, an entrepreneur in the 2000s, came back to Oracle for a while, and then joined AWS in 2016. So in my career working with customers, I've learned a few things about what they want from their databases. They want durability and reliability, they want performance and scalability, and they don't want to lose their data. Now, to ensure they don't lose data, we've invented lots of technologies over the years: disk mirroring and stripe and mirror everywhere, CRC block checks, replication, both logical and physical, log streaming, and others. And all of those technologies were invented before the cloud came along. And with the advent of the cloud, customers have started to focus on ensuring their workloads are resilient, not just within a single data center or across data centers that are close together, but also across multiple regions, while also leveraging the globally distributed infrastructure available in the cloud. So in AWS, we organize our data centers into what we call availability zones, and we organize multiple availability zones into regions. And each availability zone consists of one or more data centers, and each availability zone is designed to run on separate power, separate networking, different floodplains, et cetera, so that any single event is unlikely to impact more than one availability zone at a time. Now, at the same time, availability zones within a region are close enough together to support synchronous actions between the availability zones with latencies in the range of a small number of milliseconds. At the same time, in addition to that, each AWS region is geographically separate from other regions with latencies ranging from tens to a few hundreds of milliseconds, depending on the distance between the regions. So with that background info on how we organize our infrastructure, let's look at how our customers are asking us to support global deployments of their managed relational databases. Our customers want to maintain multiple copies of their databases in regions separate from the primary region to provide disaster recovery support, or in other words, protection against loss of access to the primary region. And in this picture, you can see the primary database on the West Coast of North America with read-only secondary copies of the database in other parts of the world. So this is a topology customers are asking us to support. But this brings up a second global database feature which our customers are asking for, and that's the ability to use the secondary databases for reads. So early implementations of technologies for global databases couldn't make the remote copies accessible. Now, as you'll see, you can use more modern approaches to create topologies like this in which each copy is available for reads, for queries, and for reports. And this can greatly reduce read latency for users who are closer to one of those secondary databases than they are to the primary read-write database. So great, so customers are asking us to make their managed relational databases resilient against regional outages and to make read-only copies of their data available across the globe to reduce latencies for their end users. So what are our options for actually doing that? Well, there's really two primary options for supporting global database deployments: logical replication and physical replication. And so to support the requirements that we just discussed, you need to have copies of the data in each region. And you need to keep those copies consistently updated with changes that are being made to the data in the primary region. Now, with both options, replication is used to copy data from the primary database to the secondary databases to keep those secondaries copies close to in sync with the primary. Now, remember we talked about latencies between regions. That latency prevents us from doing synchronous replication from the primary to the secondaries. Otherwise, the transaction latencies on the primary would be too slow. That means the secondary copies will always lag behind the primary. Changes committed on the primary might not be visible in the secondary copies for tens or hundreds of milliseconds, or sometimes even multiple seconds, depending on the implementation and the distances between the regions. But let's dive into logical replication first and talk about customer use cases that can be solved with logical replication, and also talk about the challenges of using logical replication. So I've worked with a lot of enterprise customers in almost every industry, and the common requirements consistently appear. Customers in telco, in e-commerce, and in financial services have implemented database solutions that support a wide range of multi-data center or multi-region requirements. And these requirements include easy migration from one region to another, easy upgrade paths for database patches and new versions with minimal and zero downtime. Customers also want to maintain multiple copies of their data across regions, as we already discussed, for disaster recovery and for redistribution. Sometimes customers only need a subset of data to be available in multiple regions, and with local reference data maintained separately in each region. And to avoid overwhelming networks and replication infrastructure, customers sometimes want to turn off replication per session or sometimes per statement if they want to, for example, update all the rows in a billion row table. And sometimes customers want to delay replication of DDL or schema changes to manage slow or staged rollouts of application upgrades across regions. And sometimes customers even want to implement active-active capabilities in which transactions can be processed from multiple regions and not just from one primary database in one region. So customers who have this combination of use cases and requirements will often choose logical replication. And so how does logical replication actually work? Well, relational databases are designed to keep data in memory as much as possible for performance reasons, while not compromising users' expectations about durability and survivability of the data in storage. So the typical relational database architecture will start with an SQL query optimizer at the top, with a transaction layer managing concurrency in database transactions, a caching layer to manage data in memory, and an I/O layer to move data from storage to memory and back. And down in storage, data is usually stored in database files and log files, where the log files contain a sequential stream of log records that represent changes to the database over time. With logical replication, changes to the database are replayed in the secondary copy of the database, either by mining the log files and transforming the log records into SQL statements to be executed on the secondary, or by using triggers on the database objects in the primary to create SQL statements that are then executed on the secondary. Now, it's easy to see how to meet some of the customer requirements we just reviewed by filtering which database objects for which you replicate changes, for example, or by managing schema changes separately from changes to data. However, there are some challenges and limitations with logical replication. It can be complex to set up and manage. You have to decide which tables to replicate. You have to ensure there are primary keys on all those tables. And because logical replication requires each transaction to be replayed on the secondary database, you have to have a database instance running on each secondary database. Replaying each transaction adds to the replication lag, which with logical replication will typically be measured in tens of seconds or even multiple minutes. In addition, ensuring transactional consistency can be challenging while supporting parallel application of changes to the secondary databases, further limiting performance and increasing replica lag for high change rate workloads on the primary. And then multi-directional replication, or bidirectional replication, or BDR, as some people like to call it, is tempting. Why not use logical replication to support active-active implementations? Well, it quickly gets even more complicated. For one, you have to decide how to manage conflicts when the same data is modified at the same time on two different databases. For example, if a user updates a row in one database and a user in another database deletes that same row at about the same time, and then those two changes are replicated across to the other side, how should the system resolve the conflict? The usual answer is last write wins, i.e. the change with the latest timestamp overwrites the conflicting change. But regardless of the conflict resolution algorithm you choose for each table, and they can be different for each table, application developers and end users need to be aware of the behavior so they aren't surprised by a deleted row suddenly reappearing, for example. Another challenge with BDR is monitoring and management. If the replication stops working or gets delayed by networking issues, etc., then tables can get out of sync. You need to have monitoring in place to detect this and to have tools and procedures and playbooks and all that to get those tables back into sync when they drift apart. And last but not least, what about DDL? If your implementation is supporting high change rate workloads on multiple active copies of the database, and you want to, say, add a column to a table or resize an existing column, can you do that reliably and safely across all copies of the database without disrupting the running workloads? There's challenges there that you'll run into with logical replication. But to be clear, I'm not trying to talk you out of using it. I've seen many successful implementations of logical replication to support distributed databases and active-active architectures. If you do your homework and do the appropriate long-term planning to ensure you have the skills and infrastructure in place, you can get it working and you can get it working at scale. But let's change gears and talk about use cases that lead to physical replication and the benefits and challenges of using physical replication. So we just now discussed logical, in which changes from the source database are used to execute the same changes on the target database, usually as SQL statements, logically recreating the transactions in the target database. But with physical replication, changes are replicated using the underlying storage system. Physical replication is usually implemented in the storage system, often blind to the database system accessing the storage. Physical replication can also be implemented with varying levels of integration with the database system to deliver better performance and consistency. So customers who have stringent disaster recovery requirements and need to minimize data loss and minimize failover time will often choose physical replication. In my experience, this usually includes customers in financial services and telco for their tier 0 workloads, where those workloads have stringent RPO and RTO requirements. And who depend upon the efficiency, especially of database-aware physical replication, to minimize their data loss and failover times. Another type of customer that typically uses physical replication are gaming customers, and they'll use it more for geo-distributing their read traffic, which helps with response time for users accessing games, where those users are often distributed around the globe, and is simply just easier to implement and maintain physical replication as compared with logical for their use cases. So, as I mentioned, physical replication can be used to protect against losing the database when the region goes down. The simplest form is to periodically copy database backups and log files from the primary region to the secondary. This has the advantage of being relatively simple and easy to implement, but doesn't provide good RPO. Minimizing data loss and a failover will be limited by how often you can copy your backups. Now, you could tweak this approach and copy log files in addition to database backups, which would allow you to keep the RPO lower. In a failover, you could restore to the point in time in the most recent log file, but recovery time will likely be increased. You'll have to restore the last backup, then roll forward through all the log files copied since then before you can bring the database out. A more integrated approach is to use storage-based replication to copy changes as they are made to the database in storage. If this is implemented without database integration purely in the storage layer, then the target databases are typically not accessible. They're only made available when the primary database goes down or when the replication is manually stopped and the secondary database is started. With this approach, changes are replicated by the storage system itself, usually at the block level, preventing access to the database because the replication isn't transactionally consistent. Data loss with this approach is typically smaller as incremental changes are replicated relatively quickly, and recovery time on a failover is really limited only by how long it takes to start up the database on top of the replicated storage. There might still be a small amount of database recovery needed. So with database-aware physical replication, the secondary databases can be made accessible for read traffic while maintaining consistency guarantees despite the replica lag. In other words, all reads on the secondary databases will be consistent as of the consistency point in time of the replica, but the data seen by those queries will lag behind commits on the primary. This is often implemented using some form of incremental replication or log replication to make the replication more efficient and to allow the secondary database to present a read-consistent view of the data. So physical replication is usually all or nothing, unlike logical. Replication of subsets of the data isn't typically supported with any physical replication implementation. Blind storage-based replication can be inefficient for workloads that only change a few bytes per page, because they typically will replicate the entire block every time. But having said that, storage-based replication is still usually more efficient than logical, with replica lags often below a second, even for regions that are cross-continent. It's also usually not feasible to support active-active with physical replication. So let's talk briefly about how we think about these types of customer requirements in Amazon Aurora. But first, what is Aurora? Well, this is our high-level, descriptive or marketing slide. I mean, Aurora is an enterprise database where we took open source projects, both MySQL and Postgres, and integrated them with our own cloud-optimized storage system. It delivers at a high level both better performance and better durability and availability out of the box, but still with simple managed database capabilities and simple pay-as-you-go pricing. But let's go dive real deep into how it actually works. We built Aurora to address a fundamental bottleneck with databases, the connection from the database engine to the storage. And with Aurora, we've divided the traditional database stack into two tiers. A database tier that's really just the traditional database engine, and a storage tier which looks very different than typical database storage systems. Database tier in Aurora writes redo log records or write ahead log records, WAL records in Postgres terminology on the network using a 4 out of 6 quorum protocol to storage nodes in the storage tier. Apart from these log records, which really you can think of as change vectors or deltas for changes to the database, nothing else is written. There are no full data blocks written whatsoever, not for checkpoints, not for cache eviction, not for background writes. Instead, the log application, which has been managed in the database engine for 40 years, has been moved to the Aurora storage system. The Aurora storage system itself is a highly parallel scale-out service in which we parallelize and scale out that log application process. Typical Aurora storage volume will contain hundreds or thousands of EC2 i3 instances, each with many CPUs, lots of main memory, lots of local SSDs. That same log apply processing, which used to live in the database tier, is now distributed and scaled out in the storage service. Among other things, this allows the storage service to generate database blocks on demand, and also in the background to continually materialize those database blocks. So in this architecture, if a database node needs a block that's not in its buffer cache, it goes to the storage tier and fetches the block from there, where the storage tier can generate it on demand if it's not already materialized the block in advance. From the database perspective, the log is really the database. How and where the blocks are materialized is no longer directly relevant. Because of this architecture, we're only writing individual diffs or deltas. And so we end up writing almost an order of magnitude less data on the network. And that's the fundamental innovation that leads to the performance benefits of Aurora. At the same time, even though we're writing less data, we're writing it to 6 different locations across 3 availability zones, which gives Aurora additional high availability and durability. Now, with that in mind, let's talk about logical and physical replication capabilities in Aurora. So Aurora supports logical for both engines, the MySQL compatible and Postgres compatible versions. For Aurora MySQL, we support bin log replication. And for Aurora Postgres, we support both replication slots and PG Logical is something we launched support for, I think, a couple months ago. So you can use these logical replication capabilities to meet some of the customer requirements that we discussed earlier, including replicating subsets of data, managing DDL replication separately from data, and bidirectional replication with conflict management, and at least in some cases. For physical replication in Aurora, we've implemented the Aurora Global Database feature. Aurora Global Database enables faster disaster recovery and more enhanced data locality than is possible with logical, replicating and distributing data across multiple AWS regions and supporting remote readers that can be promoted quickly for fast DR. Aurora Global Database also brings data close to your customers so they can operate with low latency, enabling you to distribute your entire application infrastructure while supporting reads in many different regions. Let's talk about how it works under the covers. To set the stage, we already talked about how in Aurora, writers are sending log records or deltas to storage. An Aurora cluster, even in a single region, can have up to 15 read replica instances. These readers consume the same log stream that is sent to the storage nodes in order to keep their local buffer caches consistent and close to the actual writer. And in practice, we see in-region replica lag of typically no more than 20 milliseconds. Now, for Aurora Global Database, in the storage layer, we have added an additional agent for outbound replication in the primary or source region, and in the secondary or target region, there's a corresponding inbound replication agent. These sets of agents, which are individual microservices in architecture, are continuously communicating, where the outbound agent receives the same log stream that all the readers inside that primary region are receiving, and it sends that log stream across regions to the inbound agent in the secondary region. This entire process has been engineered by us to operate in our WAN environments across continent, across the ocean, around the world, while still maintaining high throughput. And that's the key. We're able to hit 200,000 writes per second with negligible performance impact while still maintaining low RPO across continent, typically well under a second. Our goal with Aurora was always to provide high throughput and high performance without sacrificing availability and durability. And what we're doing with Aurora Global Database is keeping that same goal while increasing availability and resilience beyond a given region to a global infrastructure. So how does Aurora Global Database provide fast cross-region disaster recovery? The idea here is to have a distributed deployment across a global footprint where you have very fast recovery, less than 1 minute RTO, to accept full read and write workloads in the event that you have unavailability of your primary region. What's really important to understand is how things work when there are failures. And so let's start very briefly with failover within a single region. You have an application with writers and readers. The writing part of the app is pointing normally to the writer or cluster endpoint, and the reads are balanced across multiple readers. This is a common configuration in Aurora. Many customers use Aurora with this pattern. When you have a failover due to a transient issue, a network issue, for whatever reason, the system will automatically choose to promote one of the readers to be a writer. And what actually happens is there's a DNS change for the cluster endpoint. The writer endpoint ends up pointed to the newly promoted writer, and the old writer, which is now demoted to being a reader, joins the reader endpoint. From the application perspective, there's almost no impact. There's a small blip, and with the magic of DNS, everything proceeds as normal. When you think about a global database, we have a different architecture. You now have to worry about multiple application stacks. Customers typically operate in one of two modes: a pilot-like mode, in which they maintain a minimum set of resources in another region that's ready to come to life in the event of needing DR. And the other is data locality, in which the customer maintains a copy of their data in a second region that's close to some of their end users or customers, and they have a fully operational application stack in that secondary region. This slide shows the second model we just described, with a secondary region providing low latency read access for users closest to region 2. It's important to note that the database is operating in 2 regions in this example, and the app stack also exists in both regions. Here, when you have a catastrophic event, we're going to show what needs to happen in the application in order to leverage the global database infrastructure. So let's walk through what happens when you have a failure in region 1. The application stack can be spun up in the event of a regional failover if running in pilot-like mode, or if the application stack is already available because it's in use for reads. Once one of the readers in the secondary region has been promoted to be the writer, then at the application level, something must be done to promote the application components to start taking writes and to start sending writes to the newly promoted writer. Once that's done, the clients that are connecting to the application through DNS redirection can start pointing to the new stack that is running in the new region. So that's how we get low RTO, or recovery time objectives. Low RTO is great, but that's not our only goal. We of course want to have global reads with very low replication latencies. And our goal is to have low remote read replica lag of less than 1 second for cross-continent, cross-country deployment scenarios, even under heavy load, which will allow customers to achieve very low RPO, or recovery point objectives, with the read replicas in the secondary regions lagging at most a few seconds behind. And with the way we've implemented global database, sending just the log records across to be applied in the storage systems in the remote regions, we're able to deliver on that goal for most workloads. Now, low RPO is important because, even if you're able to quickly resume transactions with low RTO, if your data is minutes or hours or days out of sync, it doesn't really help to be back up and running quickly. So, the combination of low RTO and RPO, we think, is what's critical for customers. All right, so we're just about out of time. I want to thank you for your attention. Happy to take a question or two if we have time, but Matthew, I'll let you make that call.
Yeah, we do actually have a couple minutes here before we get started on the next one. I don't see any questions in the Slack chat, and I have not been monitoring the YouTube because I was told that we were just going to be using the Slack chat. So I don't see any questions there, but I do have a couple for you anyway that I came up with. The first one was, you had mentioned that physical replication can't handle subsets of data. Could you maybe elaborate a little bit on that?
Yeah, so there's a couple things there. The blind storage-based physical replication doesn't really understand what it's replicating. So it just sees changes to blocks and files in storage and replicates the changes. So kind of the original old style way of doing replication, storage-based, there was no chance of it understanding anything about what it was replicating. But even the more database aware approach, like we're doing in Aurora Global Database, it's challenging to do the right kinds of filtering without having a real major performance impact. And so, well, I won't say it's impossible. It's not been a high demand feature for what our customers are asking us for. They've been asking us, like I said, like I've described, to deliver low RTO, low RPO to meet their DR requirements and their geo-distributed read requirements. But so far we haven't seen a high demand for that kind of filtering for global database requirements, at least not for physical replication.
Okay. With this global architecture, you basically have full copies of your data set basically all over the world. How does that compare to somebody who's trying to do like a sharded solution instead?
Yeah, so yeah, we all know there's a bunch of different solutions out there that do various ways of sharding and subsets of data. And I didn't want to include that in this presentation because then it would take too long. But basically, yeah, the way I look at sharding is, you can decide to shard tables and put different subsets of your tables in different databases. Some of those databases can be in the same region, some can be in other regions. You still have to think through replication ideas, replication options, because if the shard only exists in one region and you lose the region, you've lost all that data. So you still need to think about replicating the shards around. And there's other complexities with sharding. They're not bad or good, they're just complexities. Every solution has its complexities. What about cross-shard transactions? How do you make sure those scale well or at least don't impact performance? What about resharding? If I have a terabyte of data sharded across 5 regions and now I got to reshard it in a different way, that can take a while. These are all interesting and solvable problems, but they are things to think about when you consider a sharding solution.
Certainly. All right. I think that's good for me. And like I said, I don't see any other questions coming in. So thank you for your time. Thank you for your presentation. That was very, very informative. I learned a little bit about the back inner workings of Aurora, so that was good.
All right, thank you.
All right, thanks, Matt. Have a good day.
You too.